Hi, everyone. So today we are continuing to talk about differential equations. We're kind of revisiting the idea of integral functions at the same time. But specifically now we're going to incorporate these initial conditions. And you've actually done a couple of problems already that deal with some initial conditions without me even teaching you that term. Okay. So I want you to kind of orient yourself here. What I've got here on the graph, this is a graph of f prime, right? This is a derivative graph. That's going to be important to keep in mind. So we don't know anything about the original function. I could ask you all sorts of things about like, well, when does the graph change directions? Or when does the graph when is it increasing? When is it decreasing? We would say, oh, well, this is all positive, so it's increasing. This is decreasing. Like I've asked you all of those questions before, but we have never up until now been able to actually find coordinates from that original graph, right? We've never been able to say like, okay, well, when x is 5, then y must be 7. Okay, we can tell you if it's increasing or decreasing, but we can't tell you specific values. And that's what this initial condition is going to be kind of the key to being able to do. So before we talk about how we're going to represent a function for f of x, let's get our initial condition kind of, and by the way, I don't know that I would always draw this. This might not always be helpful to draw, but I think it's going to make my point for this first question. And you'll see I added some blank space here because f of 1 equals 10 goes way up my graph. So what I know about my original function is that at x equals 1, the y coordinate is equal to 10. It probably should be even higher than that, but let's just pretend this is, continued, and this is at 10. Okay, so this is what I know, that I have this point here. Oh, let's pretend that's a straight line. Okay. Um, if I want to find other points on the graph, this is the only point that I actually know. What I can do is use the information that I have from the derivative to figure out how much is my graph changing from place to place. So for example, when I travel from 1 to 3, all of this is a negative derivative, right? So I know that some way, somehow, this graph is going to decrease, okay? I don't know how much it's going to decrease by. I can figure it out, but I know that my graph is decreasing, okay? I know that if I go backwards, this graph is all positive. Um, let's see. I guess I don't want to go that way yet because that's in a negative direction also. That's going to get confusing. But let's focus on this question of how would we find f of 3, okay? If I want to figure out how much it decreased by, remember that's what integration tells us. Integration or antiderivatives tell us how much did it change by from place to place. And in a function like this, that's what this area is going to tell me. Okay, that's going to tell me how much total change occurred between 1 and 3. And it's negative area, which means it's decreasing. Okay, so I would look at this area, and I scribbled all over it, of course, but my base is 2, my height is 1. So 1/2 times 2 times 1 is just an area of 1. Because it's underground, that's a decrease of 1 unit. So when I get to where x is equal to 3, I know that my y value has come down by only 1 unit. Okay. Now, I can't say for sure that it's going to just make a nice happy straight line. In fact, it probably doesn't. It could do something like this and drop really fast and then, level out or something like that. Like I don't know what it looks like in between. But I can figure out how to get from this point to this point because that's what this area function is telling me. Okay. And this is kind of what I was talking about before too, is that this half of the graph, if I'm starting at 1 and walking backwards, yes, it's living above the x-axis, but if I'm starting at 1, all of this would count as negative area 2, right? This would all be decreasing. So I could find this area and figure out like how much does this decrease by the time I get to -3. Okay. And let's say just, I don't know that it's actually at 3, but let's just say that that's my point. If you start here, it should make sense to you that from here to here, my function is increasing to get to that 10, and then it's decreasing to get down to that 9, and then this would represent another tiny little increase, okay? So my integral is telling me how much I changed by. So when we think about how would we write an equation for what this function is doing, okay? I'm going to say f of x is starting at 10. I'm going to use that 10 as my initial value. Okay, so I'm because this is my point that I always know is true. I can always come back to that as sort of my true north here. And then if you think about how do I represent this area that I found, well, that's an integral from 1 to 3. If I think about going backwards, that's an integral from 1 to wherever, 1 to -3, 1 to -1, or so on. So I'm going to say that I'm going to start at 10, and then I'm going to change by whatever the integral is from 1 to x, and that's of f prime. Okay, so again, just so you understand my pieces here, I'm starting at 10 because that's the condition that I started with. And then my integral starts at 1 because that's where this is anchored, right? And so then I'm measuring area from 1 to wherever to tell me how much am I increasing or decreasing by from that 10. Okay. So let's look at some of these questions. I'm going to get rid of my picture here because, again, I don't know that the picture is always super helpful, but being able to write this equation is going to be really essential. The first question is just f of 1, which is dumb because it gives me f of 1. So that is just 10. F of 3, we just figured this out, but let's figure it out kind of the mathematical way. If I wanted f of 3, the equation I would do is I would say I'm going to start at 10, and then I'm going to figure out the integral from 1 to 3 of f prime. So that's 10 plus, and then my integral from 1 to 3, that's this area that I found, right? The integral is the area. And so that area was 1, and it's underground, so it's going to be a -1, and that's equal to 9. That was that dot that we drew at 9. Okay. So let's go ahead and figure out what their -3 is. Again, I'm starting at 10. This time I'm integrating from 1 backwards to -3 of f prime. Whoops, forgot my prime. Dx, which means I'm starting at 10. If it's more helpful, like even here, this is technically a subtraction, right? I mean, we can always say it's addition, but with this integral comes out negative, you're really subtracting. Okay, and that's what's going to happen here is this integral, this is positive area, but I'm going backwards from 1 to -3. So this is going to end up being a negative something. Okay. My area here, this is a radius of 2. So I'm going to say pi times 2 squared. So pi times 4, and then cut that in half because it's a semicircle. So 10 plus -2 pi, otherwise known as just 10 minus 2 pi. So remember, I drew this star here and said I wasn't totally sure exactly where that's at. This is like 10 minus 6-ish, right? A little more than 6. So this is going to be a little less than 4. So actually, I wasn't too far off. It's going to be 3 point something there. Okay, be careful here. F prime, that's this graph, right? This graph is f prime. So this is throwing you back into some of those questions we've done before. But if I ask you for f prime of -1, then all I'm doing is reading the value off the graph, which is just this right here. I'm going to just say that's at +2. So these are all coming just, let's see, these 3 are coming right off the graph. So f prime of 2 would be at -1. F prime of 3 would be at 0. Okay, those I'm just pulling right off the graph. Okay, if I have f prime, and by the way, this graph is exactly the same. I just did this so that as I scrolled, we could still see the picture. These, how you get a second derivative if you're looking at the first derivative graph, that's a slope. So f double prime of 3 is what's the slope at this of this segment right here. This is up 1 over 1, up 1 over 1. So this has a slope of 1. Whoops, I meant to switch colors here. Messing up my whole system here. So my slope here is 1. f double prime at -1, that's this point right here. So what's the slope of the tangent line? Well, that sure looks like a change in direction to me. It looks like it'd be a horizontal tangent. So I would call that 0. And f double prime of 2, slope right there, that's a change in direction, but it's a sharp corner. F double prime of 2 does not exist. Okay, so now some familiar questions for you. Locate the critical points of F. And remember, I told you when I ask you questions like this, ignore everything else that you're seeing in front of you and just ask yourself, how do I find critical points? Critical points are when f prime of x is equal to 0. So where is that happening? I'm going to ignore endpoints. Okay, I don't have to worry about critical points at endpoints because I don't actually have a change in direction happening there. You can't take a derivative there. So my critical points would be where my derivative is equal to 0. That would be here and here, right? So I have critical points at x equals 1 and x equals 3. Are these mins, maxes, or neither? Well, remember what we want to look at is how is my derivative changing? Here I have a positive derivative that changes to a negative derivative. So at x equals 1, that must be a relative max because this part of the graph is increasing, this part of the graph is decreasing. X equals 3, this is going from negative to positive, so this must be a min. Okay. And let's go back up here to my picture for a second, my really fake picture. Actually, next page notes. Here we go. Let's see if I can line this back up. Okay, what we said is that the points we know about is that this one would actually be probably a little bit higher, but right here I'm going to have this point just above 3. I've got this one at 10. I've got this one at 9. And then at 4, I'm going to have to have increased a little bit because this is all positive area, right? So my next point is up a little bit, okay? So again, I don't want to assume that these are all just perfect straight lines, but if you picture this, if I'm here and all of this is positive area, that means I'm increasing up to that 10. And then this is negative area, so I'm decreasing down to that 9. And then I'm increasing again, okay? So make sure that checks out with you as far as where your mins and maxes are. It makes sense to me that this is a maximum because if I'm reading along this graph from left to right, all of this is increasing. This whole semicircle, that's all positive, right? So all of this is increasing, and then it hits this little section that's decreasing, and then you must have a minimum here because then you start increasing again, okay? So don't assume that you've got nice, perfect straight lines here, but you can assume that you're increasing and then decreasing and then increasing again. Okay, so that should all kind of just check out. Okay, and on what intervals are we decreasing in concave up? Okay, so this is a throwback. This is nothing new, really. I'm looking at f prime, so I want to be thinking about how do I tell from f prime? Well, we're decreasing when f prime is negative, and we are concave up when f prime is increasing, okay? Because if f prime is increasing, then I have a positive second derivative, and if I have a positive second derivative, then I'm concave up. So I'm looking at when am I negative, but also increasing, and I think there's really only one place that that's happening. This little triangle is the only place that I'm negative, and then this is the only chunk where I'm increasing. So from, what is this, 1, 2 to 3, okay, would be my decreasing in concave up. Okay, and again, this is my reasoning. So a lot of the same stuff you've seen before. I think the newest thing is how do you actually find these values? I couldn't ask you this before. Okay, I couldn't ask you to find actual function values, but now I can if I give you an initial condition. I have to give you an initial condition for that to work. Okay, let's try another type of example that kind of incorporates the same idea. So we've got some particle motion going on here. Um, so what I've given you here is an acceleration function. I want to make sure we understand that what we're looking at is acceleration. Okay. Um, at time 0, and I don't have to give you 0, I can give you other times as well, but this right here is giving you an initial condition. The velocity is negative 9 feet per second, and the position is negative 27 feet. Okay, this is like a 2-in-1 problem. All right, there's a lot of information here, but what I want to make sure we understand is that all of this is outlining initial conditions. Okay. So if I have acceleration and I need to get to velocity, that's the antiderivative process, right? If I'm at acceleration and I'm trying to get to velocity, I'm going to do an antiderivative. So I have a of t is 6t plus 6. My velocity function is going to be my integral or my antiderivative of 6t plus 6. Okay, well, let's take that antiderivative. So I'm going to add 1 to the exponent. That makes a 2 and then divide. So this is now 3t squared. The 6 is going to become a 6t. And then right now, this still has a plus c hanging out at the end, right? But this is where my initial condition for my velocity comes in. So what my velocity is telling me is that when t equals 0, the velocity is negative 9. Okay, so I'm going to have a negative 9 velocity when my t is 0. So if I put zeros in here, I'm going to get 0 plus 0 plus c. So essentially, that c is negative 9. I do want to make sure that we're being cautious about this because you might assume that just whatever number this is just going to be your c value. That only worked out because I started you at time 0. If I started you at time 5, if I gave you that as an initial condition, you would have to plug these numbers in and do some solving. It wouldn't be hard, but you would have to solve for it. Okay. So I'm now going to officially say that my velocity function is 3t squared plus 6t minus 9. Okay. We couldn't do that before. We couldn't get all the way to the equation. We would have to stop here. We could say it's this plus c, but the new thing is, can we throw in that c value? So now let's do it again. Now we're going to find the position function, and the position function is the antiderivative of the velocity, right? So I'm going to do this very much the same way as what I just did. I'm going to start with my velocity function. I guess I probably didn't need to rewrite it, but I was trying to match what I did up above. So if I want my position function, that's going to be the integral of b of t, which is, so let's add 1 and divide. So that's going to give me a t cubed. Add 1 and divide, so that's going to give me a 3t squared. My negative 9 is going to give me a negative 9t. And then because it's a general antiderivative right now, it's going to have a plus c. And once again, I'm going to use that information from the initial condition. I know that when time is 0, my position is negative 27. This is going to end up being just like this one. My position is negative 27 when my time is 0. So all of these are zeros. So negative 27 is c. And now I have a position function. So my position function is t cubed. I'm probably rewriting a lot of stuff that I wouldn't normally need to rewrite so many times. I'm just trying to make it so that we can follow it later. Minus 27. Okay. These questions now are all old. All right, these two questions here, you've seen these before. On what time intervals are we moving to the right? The question we want to know here, what we're asking ourselves, is about the velocity, and I want to know, when is the velocity positive? Okay. Well, first, to figure that out, I need my critical points, which means I need to know, when does my velocity equal 0? So I'm going to take my velocity function, and I'm doing this calculator free, by the way, 3t squared plus 6t minus 9, and I'm going to make this thing equal 0. Okay. I'm going to pull out a 3 just to make my life a little easier. So then I get t squared plus 2t minus 3 equals 0. Let's factor. Did it again. Sorry about that. There we go. So this is now t plus 3, t minus 1. I think that works. And so the answers that I get are we have a velocity of 0 at -3 and at +1. And I actually don't care about this -3 because in this context, having negative time does not make sense to me. Okay, so the only critical point I have to worry about is +1. So here's my number line. Starting at time 0, this is time down here. Okay, and then I'm going to put 1 on here. And what I want to know is when is my velocity positive? Is it between 0 and 1 or is it after 1? And here's my velocity function. If it's too hard for you to plug numbers in, like I'm going to have to choose something like 1/2, I think. And then maybe a 2 here. If it's too hard to plug in here, plug it in here. Okay. If I put, so this is always positive, right? If I put a 1/2 in here, 1/2 plus 3 is going to give me something positive. But 1/2 minus 1 is going to give me something negative. Okay, positive times negative, that works out to be negative. Let's do it again with the 2. This 3 is always going to stay positive. If I put a 2 in here, 2 plus 3 is 5, so that's positive. And if I put a 2 in here, 2 minus 1, that's also going to be positive. So over here, this is all going to be positive, which means all of this is going to have a positive velocity. And so to answer my question, I would say on the interval from 1 to infinity. Okay. Everywhere after 1 second. And I don't think it gave me a limit on how far. Yeah, it just says for time greater than 0. So, okay. Speeding up or slowing down at 3 seconds. You've seen this question before too. Okay. For speeding up and slowing down, what I want to know is what's happening to v of 3 and what's happening at a of 3. And again, if you don't want to crunch the numbers all the way, all we really care about is if this is positive or negative. Okay, so I'm going to look at my velocity function, which is up here. I will crunch the numbers. I'm probably going to use this factored version. Okay, so if I plug in a 3 for my t's, I'm going to have 3 times 3 plus 3 is 6 times 3 minus 1 is 2. And I'm not even going to bother multiplying that all out. I know that that's going to come out positive. Okay. My acceleration function is going to be 6 times 3 plus 6, also going to be positive. So I would say speeding up because both of these are positive. Speeding up in a positive direction. Okay. So that's just kind of taking old stuff, adding a little bit of new to it. Shouldn't be too terribly difficult for you, but if you do have any questions, as always, feel free to ask.